Welcome. Let me say something more about this partial differential equation. This week it occurred to me that this partial differential equation, this modified wave equation, is related to the Black Scholes equation, a beautiful partial differential equation which is important in finance. It should be on this list of most important formulas, and it became famous it was introduced in the 70s but became famous in 2000. There was a movie about it. Maybe I show a clip from this movie. And then in 2008, after the crash, the house market crash in 2008, Hollywood jumped on it and produced two movies, The Margin Call and The Big Short, which illustrate the craziness of all these schemes. So I'm sure that all this money, this quadrillion, one thinks now there are quadrillions of derivatives, and actually this deals with derivatives, so it is a completely different type of derivative. This is a quadrillion-dollar question. Partial differential equations are very important these days. In a few years all my money will be gone, things will evaporate, but this theorem will stay. Mathematical theorems are forever. They are also in thousands of years. That's my consolidation. Anyway, it's, I think, a beautiful result on wave equations. If you look at the classical wave equation, this is the explicit solution which D'Alembert wrote down. Usually this is written down using pseudo-differential operators by the square root of the scalar Laplacian. I'm looking at it on all forms, differential forms which are 0 forms, 1 forms, 2 forms, until q forms in q dimensions. And so you have a beautiful wave equation there, and this is the solution. But this doesn't satisfy the Higgins principle. So the solutions in even dimensions, they have wakes. So in odd dimensions, like in our world, this works. Now, this is the modified wave equation. I decided to write it down in a modified form by just redefine the acceleration. So if you look at this thing, this depends on q. For q equal to 1, it's the usual acceleration. For q bigger than 1, this is kind of a modification which for larger time t becomes negligible. So this is kind of going to 0. So asymptotically this looks like the usual wave equation, and it also has the usual solution, the usual Newton law if the acceleration is constant. So you have quadratic growth. So all the things hold also here, despite this singularity at t equal to 0. But t equal to 0 is not something we are actually interested in. We want to get rid of this, derivatives. We want to get just differences. And I'm defining here, defined now since, the whole spring semester so far, and the whole winter I thought about this, and I started to think about this already in 2010, just around the time of the crash, but it was not related. But what happens is that there is a nice derivative here, which is a bounded derivative, and it, like in dimension 1, it just only depends on the values in distance t, or distance h, if you would think about h as your Planck constant. So we are pushing away everything away from the point, so that we have no derivatives anymore. We have just differences. And but it's based on classical mathematics, old mathematics. Like we started actually with this averaging over spheres, over balls, and I talked about this oval article here. This is actually a result of Pizzetti from 1909, and it shows that because of Stokes' theorem, it shows that if you look at this equation here, that's kind of the upshot is this equation is satisfied by this explicit by this solution. We cannot take at t equal to 0, the position has to be 0 in order that the wave equation makes sense, but the initial velocity can be given, and it's just the gradient at t equal to 0. So, but we have an explicit solution here. This exterior derivative at time t is actually a solution of a wave equation. And I was puzzled, you know, since many years now, why this Bessel here, if you look at that, it's not the Bessel function which comes in dimension q, but q plus 2. That was a little bit strange, right? We have these equations here, this Bessel equation, which comes from when you spherically average the Laplacian in q dimensions, and then these functions here appear important in classical mathematics, and so in spherical coordinates they come up. But why does the q plus 2 here come up if you do the sphere averages? So that's kind of my observation here. I was observed that this is just Bessel, these are Bessel functions. But I was puzzled by the fact that we have q plus 2 here. And it kind of becomes clear if you look at this wave equation here. And so this wave equation kind of explains why the q plus 2 comes in. And this computation, I struggled a little bit 2 weeks ago about this. And 3 lines of Mathematica code kind of just show you that this solves this wave equation. So what I originally wanted to talk about is about the technical detail which came up last time. Again, I kind of tried to address it several times already. What we have done with this sphere averaging, we have only shown it for q-1 forms, right? So that this is a kind of a q form, a volume form. And so that, and then we want to push it down for the other form sectors. We want to have it for q-2 forms, etc. I thought about it a little bit more, and I thought maybe the inner derivative, another derivative different from the finance derivative, right? The inner derivative, which is kind of an important notion in differential geometry and Hamiltonian symplectic geometry, etc. This Cartan formula is very, very important. So this is the Lie derivative and this is the exterior derivative. The Ix goes down in the sectors, right, from k forms to k-1 forms. The D goes up from k forms to k plus 1 forms. So Lx stays the same. That's kind of just the Lie derivative. That's kind of like you let it flow. You take a vector field and let the form flow and see how it changes. And so this rate of change. And that's kind of a little bit, so this allows then to switch the D and the Ix. That's important that we can switch that, but that switching is only possible if the Lx is 0 for the form. So my puzzle was to actually write any differential form as a linear combination of differential forms Ix G of one, sector higher, and so that it is Lx invariant. And this can be done. It's just an algebraic tool can be used, which is called polarization. And that brings me to something else, which I'm very fond of, polarization. If you look at that, I always use this in multivariable calculus or even differential geometry. The Ricci tensor is determined if you know Rxx, right, for every x. Or the metric tensor is determined if you know Gxx. So a bilinear form is known if you know the bilinear form for VV. You don't get all the off-diagonal terms you can get from this polarization. This is called the polarization identity. It's also known as the parallelogram identity in dimension 2. So this is how usually you see that. But we need a higher dimensional version, and I found a higher dimensional version. It's kind of a little bit hidden in the literature, and but it's true in any commutative algebra. It's kind of a beautiful identity. I love this identity. It's kind of what you do. You write every monomial. Of course, it's enough to use monomials. So you have any monomial you can write as a linear combination of monomials powers of something else. So that's important, so that we can then take a vector perpendicular to that and kind of have the Lie derivative in that other direction. So that's kind of a beautiful identity. Let me just quickly show you why this is true. When you look at this expression here, this is symmetric. This is completely symmetrized. So what happens when we symmetrize that, it should be just a multiple of that. But in order to find this constant here, which is in front of that multiple, we can just put the x1 equal to 1, x2 equal to 1, in a ring with 1, and we can then get an identity with binomial coefficients, which can be simplified to n factorial 2 to the n. And that's this polarization identity. So I hope to finish this project at some point. That's it for today.